I'm Jithin. This is my friend Sid. We are game programmers from Sumo Video Games Private Limited. Sumo Video Games Private Limited is a subsidiary of Sumo Digital. We are founded in 2003 at Sheffield in England. We are licensed developers across all Microsoft, Sony, and Nintendo gaming platforms, and our expertise lies in developing and growing licensed IPs. Coming to studios, our headquarters is in Sheffield, and which is at England, and we have a couple of more studios there. We have one at Nottingham and one at Newcastle, and the recently acquired Chinese room in Brighton. And in India, we have a studio at Pune, which is where we both are from. If you see, these are our couple of titles that we released over the time. And if you see, we have some of them are AAAs, and the recent ones are like Hitman and Forza. To talk about a bit about Sumo Video Games Private Limited, which is the Indian branch where we both work at. We are established in 2007, and we work alongside Sumo Digital, which is one of UK's largest independent video game developers right now. So together we have quite a long history of developing AAA titles for platforms including PS4, Xbox, Nintendo Switch, PC, and we are partners with obviously Sony, Microsoft, Sega, Codemasters, EA, BBC, and a lot more. In 2017, we have released our first self-published title, Snake Pass. If you guys have been here in the last years, GDC would have probably met our team. Coming to Pune development team, we started at 2015 with just 6 people. Right now we are 15 and counting, and so we are expanding. So to accommodate this expansion, we have moved on to a bigger and a better studio right now. And we are co-developing with our UK studios. It's not like we are independent studio that makes game right just in Pune. It's not that case. We actually co-develop with them. And you might already know that we work exclusively on consoles as of now. And there is exciting and organic growth potential out there. Let's move on to the talk, making your AI to behave. What's a general AI behavior? You would say AI behavior is the process of making any non-player characters to think and act as if it's an intelligent player character. So it's basically making your AI to mimic a human player. So the thing is, when I talk about AI behavior, people tend to think the complicated aspects of it, like deciding that final move in your chess game, in that late chess game. It doesn't have to be that complicated. An AI behavior could be something as simple as moving from point A to point B. It's something that comes so natural to us humans. It's so mundane, we don't even consider it. But that's not the case with AI. So moving from point A to point B and being smart about it, as in like choosing the shortest path to reach there or the safest path to reach there, and not being utterly dumb at it, as in like not bumping into an obvious obstacle right in front of you. That's pathfinding. That's an AI behavior. It's a classic example for an AI behavior. And then making your AI sensitive to his surrounding. That is like making your AI, giving him vision or like auditory and olfactory or like tactile senses. That's your perception. That's another AI behavior. And then again, making your AI aware of the lay of the land or his surrounding, basically like making him decide what's the best spot to hide and take a shot at his enemy at the same time, basically making him know who has the high ground. That's spatial analysis or tactical positioning. That's another AI behavior that people tend to overlook. And then if you had played any open world game, you would see masses of crowd all around the world populating it. As if there is a purpose for each and single civilian to be at a place at a particular time, interacting with other crowd members, being quite natural about it. That's crowd simulation, one of the most beautiful AI behaviors I've seen. But we are not here today to talk about all these stuffs. We are here to talk about action planning, which is at the heart of any AI behavior. Action planning is basically deciding what to do in future. But Before we go and dive into action planning, I need to take a small detour and make yourself comfortable with another topic, which is the AI cycle. It's also called as the robotic paradigm or the sense, think, act cycle. So you take any AI controllers that you have, be it a small microcontroller that controls the temperature of your kitchen oven, or the AI controller for the biggest, baddest, meanest boss that you have designed in your game. They all has to go through this cycle. They have to sense, they have to think upon that, and then they have to decide an action to do and do that, and then keep repeating that. Because this concept is so important and it intervenes to most of our upcoming topics, I'm going to take a bit of time and going to dive into each of these. Let's go into sense. What is sense? Sense is, obviously, you have your basic sense, you have your visual sense, which in terms of games is probably your visual cone, right? And you have your auditory sense, which again in game sense is probably just a sphere around the player character, within which you would assume that you can hear anything that's approaching him from any side. The same goes for olfactory sense or the sense to smell. Maybe like if you're making a dog AI or something, say buddy AI, there's a sphere around him, and then anything that comes in that sphere, we assume that he can smell him. For your tactile sense or the sense to touch, we would, in terms of gaming, we will have a player capsule around the character, or a character capsule for that matter. Anything that touches the character capsule, we would assume that it's touching the player, right? So this becomes your basic senses. And then we have game state awareness, which is not actually a sense in its purest sense, but it's probably a brain fact. But for simplicity's sake, we'll consider it as a sense right now. So what is game state awareness? It's like knowing some aspects of the world that you are in. For example, like what time of the day is it? Or what day of the week is it for that matter? What team am I playing in? And who are my enemies? Such stuff. So the primary responsibility of the sense state is to collect or gather raw data from different senses, right? From your sight, from your smell and all that. So it just collects the data and writes to a particular place, which would be assessed later. Let's give an example, because that makes it clear. Let's consider we are doing an AI for a cricket batsman, and his visual sense, like his sense to sight, would tell him the posture of the bowler, the physical location of the ball, and how speed is it coming at. And his game state awareness would tell him like what kind of pitch is he on, what over of the game is it, how many wickets are left, so he can make some decisions based on this. The next part, the part that actually uses this data, is the think part. Here, you take all that raw data, which by itself is not meaningful, and process it to arrive at an information, or basically this is where you make an informed decision based on the data that you have collected from the past. So this state is responsible for what do you say, concluding all the data that you have collected to an action, right? We'll again come back to a cricketer example. So in the last state, he has seen the ball coming, and he know what over he is and all that details. So from here, our think state would either decide to like make a strike, or be defensive about it and like do nothing, or assume a defensive stance. So whatever it is, the output is always an action or a set of actions. Now, what's an action? An action is a concrete step that you can perform, right? It's something that you can always do. So an action could be synchronous or asynchronous, as in there is no such rule that action would be completed in an instant, right? Take an example of, again, moving from point A to point B. It is usually done over a duration of time. Like he has to pathfind, he has to actually do the locomotion and move there. It's not something that happens in an instant. So unless you're teleporting, of course. So anyway, all actions usually have a result. It could obviously succeed or fail, or it could be an intermittent state that is like executing, right? Like being processed right now. Again, since the very behavior of an action is to perform something, this could end up changing the state of the world. So you see how this goes, right? Like a state change in the world makes the sensors to collect data, and the thing state to actually process it and arrive at an action. And performing that action causes additional changes to the world, and it's a feedback loop. It goes on, goes on, goes on, and that's how you have a very receptive AI, right? So again, coming back to the cricketer example, let's say that our planner or thinker has decided, okay, it's safe to make that strike, okay, and let's go for a sixer or something. So what happens? You would say, take the strike, but it's not that simple. It's not just like take the strike, because you probably would have to break it down to sub goals. That is like maybe like keeping your left foot up and assuming a stance and then actually making the strike. So done in a sequence, it's taking that strike. So anyway, being that out of the way, let's come back and talk about action planning. So yeah, what is planning? Planning is basically deciding what to do in the future based on data you have arrived from the past. And there are certain rules and constraints that affects it. And outcome of planning is usually a set of actions to be done. An action, at the same time, is an executable step, like I already mentioned, like moving from a place to place, or playing an animation, or playing a sound, changing a game state, could be anything. I'll give it one more example, because this point is kind of important. Let's take an example of an animal grazing. So Mr. Bunny is hungry right now, and he has 3 potential grazing areas around him. And let's assume that each grazing area has an attribute of threat associated to it and an attribute of resource availability associated to it. The bunny would have to make a decision based on like these 3 factors. So his sense state would contribute towards knowing the threat level of an area, or the amount of resource availability in that area, and the proximity, how far that area is to him. And his think state would, after considering all this information, his think state would decide, okay, I'll go to point A, because there's good food there, it's probably near, and maybe there is not much predators at that point. Based on that, he would actually have to do the grazing now, or like having to consume the food. And it's not a single, even though it's a single word, it's not a single step. You have to actually move to the destination. You have to execute this locomotion. He has to do his pathfinding. And once he reaches there, he has to actually start eating. That's the act part. Now, this thing could actually cause further changes to the world that might result in more and more actions. So what did we do just now? This is what you call as designing a behavior. You just design the behavior of a grazing behavior of an animal. So do we have any tools to do this? Do we have any tools that helps us do this? Yeah, we do. That's called as AI authoring tools. And a classic example is your finite state machines. I'm pretty sure most of you guys are used to it. Finite state machine was once the, state of the art AI tool up there. But right now I've seen finite state machines creeping into even UI apart, not just AI. So this is where you have multiple states, and you let your player character jump from one state to another based on different transition criteria, right? And then we have a more recent child in the field, that is hierarchical finite state machine. The new Doom uses this. It's basically finite state machines, but with a level of hierarchy in it. And then we have behavior trees. Actually, we are here to talk about behavior trees. But before we go in there, let's just consider an example done in both finite state machine and behavior trees. So here is an example of a simple vendor done in finite state machines. Our vendor would just stand around idling. Maybe he would wander around if no player or characters is nearby. But if a player character approaches him, he'll probably greet him and then probably open his a menu, and then maybe try selling some stuff to the player, or buy some stuff from the player. And then once the player interaction stops, you would probably greet him and get back to his business. So if you see here, you would see that there is a lot of transition happening, and there is a lot of backtracing happening. There is some, for example, take idle state. There is a lot of transition from and to idle state. So when you have to debug this thing, in the middle of a late night crunch, it's not going to be simple because it's quite difficult to trace out from where the execution is coming over to where, right? Now I'll show the same example with behavior trees. So this is the same thing in behavior trees. As you see, it's a tree. So the rightmost part of it, the sequence, is idle behavior. You'd see that if player is not there, you would probably idle, and then if once idle is done, he'll probably wander and keep repeating that. At the same time, his leftmost sub-branch is for what to do when a player is there. You know that it's in quite a good sequence. He'd first greet the player, and then he would open the store, and then he would try to buy and sell. If there is no backtracing here, it's a tree, there is a defined way the control can go, and when you are debugging this, you are not in problem of trying to identify from where the control came here. Now, behavior trees, right? So why do we have to use behavior trees over FSMs, that is? So behavior trees are quite easy to be laid out for your game designers, your AI designers. It's visually a tree, so you can easily make decisions based on that. So anyway, it's quite easy to follow the execution flow of the behavior tree. That's another thing that I love about it, because when you are debugging it, you always know that, okay, if a child node is active, then it means that the parent nodes of these particular child, you can trace it back up to the root tree. So it's quite easy to debug. And another thing is that behavior trees helps you to handle otherwise unhandled cases which happens when you do with FSMs. Because in FSMs, when you make a transition from a state to state, there is, based on a condition, you probably and mostly at times miss what should you do if that condition fails or something like that. So, but in behavior tree, it's a tree structure. There is always option A and option B. If A fails, there is always an option B, and you don't miss it, right? You don't miss to plan that part. That's one of my favorite takeaway. And talking about the structure, I mentioned you that behavior tree is a hierarchical collection of nodes, and we have 3 types of nodes. We have composites, decorators, and leaf nodes. So a composite node is a node that can have 1 or more children, and it usually executes its children from left to right or right to left fashion, depending on the behavior tree's implementation. The decorator is like a composite, but it can only have a single child. They are usually used for conditional executions to decide if control should flow into a particular branch or not. And then leaf nodes. Leaf nodes is a node that cannot have any child or any children, and they are usually used to execute an action, right? So basically, composites and decorators are used for arriving at the right leaf nodes. And the control flow of a behavior tree always starts from the root, and it trickles down in a depth-first fashion, and every parent of a currently active child gets ticked, and any conditions on them are evaluated, and if fails, it could end up aborting the currently active child. Right. We will talk about the composite nodes now. Sorry. So first one is sequence. A sequence is a composite node that we use when we have to perform actions like in a sequence, one after other. So for example, let's take an example of a sim, right? We are developing a simulation game, and let's say that our sim has decided that he is hungry. Now what to do when he is hungry? What he would do? He would walk up to the fridge, he would open it, and he would try to get his favorite pizza leftover from yesterday, right? So that's our sim. Anyway, so this thing has to be done in a sequence. So he has to first move to the fridge, get the food, again take the food back to the table and eat. If any one of this child fails, he's going to go hungry. He's not going to get food. Because if he cannot reach the food, there is no question of getting it. If he cannot get the food, there is no question of moving it to the table. And if he cannot get to the table, he cannot eat. Right? So the sequence succeeds if the last child of the sequence succeeds, and it fails if any of the children fails. We have a complement to this, which is a selector. A selector is like sequence, but A selector is considered to be a failure if the last child of the selector fails, and it's considered to be a success if any of the children of the selector succeeds. Selectors are used to kind of branch into different modes, different trees, different subtrees, that is. Let's take an example of our sim again. So this next day, he has leveled up and he's hungry. So his first instinct is again to go to his fridge and grab his favorite pizza leftover. So he tries that. He walks into the kitchen, he moves to the fridge, he opens it, he tries to get food, and wham, it fails because there is no food. That's because his roommate probably ate it without him knowing it. So that's there. But now what? No, but our sim has leveled up. He has a neat trick up his sleeves. What he does is he just start going and preparing his own meals. So if you notice from the last slide, the sequence of preparing food, the sequence of getting the food from the fridge is not directly connected to the route. Instead, it goes through a selector, which means if the first part fails, that is, if he couldn't find a food in his fridge, he would then try and make his own food, right? So yeah, in that sense, he would try preparing the ingredients, cook, and get that food. If he get the food, in either way, he would just move to the table and start eating it. But if this also failed, the sim is definitely going to go hungry. We'll have a grumpy sim. We don't want that. Right, anyway, parallels, another set of decorators. Composites. So a parallel is used when you want to run two subtrees at the same time. When I say same time, it doesn't always mean multi-threading or multi-programming. It just means that both the subtrees get executed in the same tick. So when do we use this? We use this at situations where we want to an example would be apt here. Let's say you want to follow the player and attack him at the same time. So the first subtree, that is follow the player, would take care of the pathfinding, make sure that the player that you are attacking is always in the correct range, avoid obstacles and stuff. At the same time, the rightmost tree, that is the shoot at the player tree, for the lack of a better term, would decide how he attacks him, like whether to use your primary weapon or secondary weapon, or maybe switch to grenade and blast him out, such. So running at parallel, this always keeps your enemy at sight and will be attacking him. So that's enough theory part of it. We'll go to the Unreal side of this and we'll see how we do this stuff in Unreal. We have Sid here to walk you guys through it.
Hi, I'm Siddhartha. So I'll be going through behavior trees in Unreal. So Unreal has a very powerful AI authoring tool, and it's also very easy to implement. So as you know, it is based on behavior trees, and also they are event-driven behavior trees. So this makes the behavior tree implementation the most optimal. This tool is built into the engine so that it has very easy access to the subsystems like your navigation system or EQS, environment query system. AI tool in Unreal consists of two parts. One is your behavior tree, another one is your blackboard. So like any other AI system, it needs a very reliable storage where it can read and write data. So that is your blackboard in Unreal. If you see behavior tree as a processor which is processing information, and blackboard is the memory which is going to provide the information to your behavior trees. Let's talk more about the behavior blackboards. So if you open a blackboard, what you see, it looks like a map or any other associative array. It's like a list of key value pairs. Information is accessed from blackboard by using these specific keys. So you write or read data using keys. So let's look at an example. Like we'll take the same example that Jithin has given. So if you're writing a sim, and if you want to know if you want to write information to a blackboard, whether it is hungry or not, you will create a key like is hungry, and its value will be a Boolean. So if it is true, that means the sim is hungry. If it is false, it is not hungry. Or we can take one more example. Like if you're writing a combat AI character, and you want to know the information about its health, like how critical its health is. So you can create a key like character health status, and then it can have a value as an enum, which has like not wounded, wounded, or critically wounded. Coming to behavior trees in Unreal, so it is actually consists of four parts. First one being your services, and then comes your composites and decorators or conditionals. So where was I? It has services, composites, decorators, and finally tasks. So let's talk about services. So services are the nodes where you actually have a periodic updates. Say for reason you want to update the blackboard, which you don't want to do continuously, you can use services to update. Let's give an example. So now coming to the same sim, if you want to know if the character is hungry or not, you can write a service which goes through the statistics of the player or stats of the player and decides whether the character is hungry or not, and it writes to the blackboard. Say you have this combat AI character. So you can write a service which goes through the health, like maximum health and the current health of the player, and it decides whether it is wounded or it is critically wounded or it's not wounded. And services can also be used for other actions which needs periodic updation. Say like you have a task where you need to repath. So your AI is depending on navigation and it needs to repath. If you know, like a repath is a very expensive operation. So you cannot afford to do it every tick. So these kind of actions, you can actually put it into a service where they happen after a set amount of time. So this actually introduce a very nice behavior into your AI system, like a reaction time. So whenever something changes, the AI will not instantly react, but it takes some time to react, and which gives a very nice and polished look to your AI. And one more common example that you can take is if your AI character needs to know if the target is in line of sight or not. So how would we do it? Generally, we use raycast. And imagine you have hundreds of characters in your game, AI characters. If each and every character is doing a raycast, hundreds of raycasts every frame, it's going to be very slow. So that kind of things you can actually push into a service which happens every 2 seconds or once every 5 seconds. Next are your decorators. We also call them as conditions in Unreal. I think Jithin has given an introduction to it. So these are like a branching for your nodes. So a condition to branch your node. So we'll take an example here. So here, if you see the highlighted part, so this is where the condition happens. This is going to read our if hungry key from the blackboard and decides whether to execute that tree or not, or that task or not. Apart from the common conditionals, Unreal also provides some special conditions. We have something called as force success node. So it's a decorator, it's a special decorator. So say you have a scenario where you have a sequence. In that sequence, all the tasks are not required. There's some of the tasks which are optional. So we'll see this example. So you're writing again a combat AI character where equipping weapon is not equipping weapon is optional, but approaching target and attacking are must. So you write a sequence, you have equip weapon, approach target and attack. So if you remove the force success, if the character doesn't have any weapon to equip, so equip weapon will fail. So entire sequence will fail. But if you want your AI character to attack the enemy even with its bare hands, you can make this node as optional by using force success. Next comes your task. Tasks are like your actions in a behavior tree. So these are the final ones. And if you see everything above the task is like your think cycle. So you have your conditionals, you have your composite nodes, you have your services, and also you can look at services kind of like a sense, which is going to accumulate data for your behavior tree. And one of the important feature in Unreal behavior trees is you can use subtrees. Like it would be a separate part. I think many of you have played like MMORPGs where you have like a very complex boss. Like imagine the kind of behavior tree for an MMORPG like a World of Warcraft boss. So it cannot be done by a single person. If you have a single behavior tree and only one person can work on it. But because Unreal provides this level of abstraction, so you can actually delegate the work to multiple people, and also it becomes very easy to maintain, and it also gives you reusability. So coming to this example, we have the same sim example here. So where you have the main tree, and the left branch is idle. Say if the sim is not hungry, then it will be doing some idle behavior like wandering around or just sitting on a sofa. So or ambient behavior, it will go to the next left side. But if the sim is hungry, then it goes into preparing the food or getting the food from the kitchen. So this is like one of the most important feature of behavior trees in Unreal. Next would be like, I'll just give you a brief like how to set up your AI character in Unreal. So we usually use a class called pawn to set up your AI character. So these is actually used for two things. One is for a character which is controlled by player or an AI controlled. So if you're writing a player controlled pawn, its controller will be a player controller where either it will take actions from your controller or from a network. And then you have your AI characters or AI entities whose controller is AI controller. And in AI controller, it has like behavior tree for its logic decision making and blackboards for its memory. So it is like a hierarchy, like AI controller owns the behavior trees and behavior trees owns the blackboards. And it's not only the behavior tree which is part of the AI controller. It also gives you extra things like it has path following component where you can give an actor and it will give you the path and you can use that to follow the player. And it also gives you option to set focus. Like you can give a focus point where the character will turn to that point and focus, or you can give a focus point as an actor and it will just focus on the character. And it also has sense components. So as Jithin has explained, you have various senses like visual senses, auditory senses. So these are also built into Unreal, and this AI controller will allow you to add those components to it. And coming to the pawn, it also has other components like your movement component and animation instance components, which are like very important, or for any general AI, you usually need animation instance or movement because the AI character that you usually write, which moves around or it changes its animation. I'll give you some pointers when you're working with behavior trees in Unreal. So first one is like, as you know, there is a problem here. When you're using selectors, you might think like, I can use selector as a conditional branch, if or else. Like, if the first branch fails, that means whatever the condition is there in the first one is wrong. So the second branch should be true. Coming to this example, if you remove the is wounded, you might think like the first sequence fails. That means the medikit was not applied, or the first medikit failed while applying. That means health. There's a full health for the character. It goes to the second sequence. But this sequence can fail at any point. Say it can fail after applying the health pack. So when you're closing the medikit, it might fail, or it can fail even before that. What if it fails when you're opening the medikit? So entire sequence fails. Your AI character is still wounded, but still it's trying to find the enemy and attack. So the best way of doing it is you need to have one more decorator on the second sequence where it checks the health status of the character again, whether it checks if it is wounded or not, then only try to find the enemy and attack. Don't use selector as your if-else branching. Next, like for a single node, you can actually add multiple decorators, like multiple conditions. And usually the conditions are executed from top to bottom, so there is an order. But, and usually these conditions are like you check something, you compare two things. So order may not always like matter, but there are these special cases like we talked, force success or loop, where irrespective of where the decorator is placed, it always executes at the end. So if you have a decorator as a second or third one, at the end it is always successful because it has a force success decorator. Same with the loop. Like if you want to iterate a task or a node for some time, like till a condition is true, all the decorators which are above and below the loop should succeed for the loop to, for the iteration to continue. Next is unregistering events whenever the node is aborted. I don't know how many people have worked with Unreal and blueprints. So the blueprints in Unreal has like a latent calls, like your delays or timers, where you can actually say like execute this function after some time. So these are actually automatically cancelled whenever a node is aborted. And one more thing is a node can also subscribe for an external event. Like for an external, whenever something changes in the game state, execute this. So if your trees node is subscribed to the external, you should always take care that you unsubscribe to it whenever the node exits. Or else, if the tree changes, like if it goes into a subtree, if the external event fires, it goes into that and it becomes a big mess. Like it will be very hard to debug. You have simple parallels in Unreal, like just like the parallels which Jithin has explained. Say like we'll take the sim example. Like if you want to make the sim wait inside a waiting room for say 1 or 2 minutes, then you can actually have wait as a parallel to the idle behavior or your ambient behavior. So it keeps on repeating. So irrespective like whether it failed or not, like it's in a room, so it has a TV, so it goes and watches TV, and if it fails to watch TV, it will try to find another ambient behavior till the times runs out for the first wait cycle. So this is one trick that we used in our company. That's it. I think I have to run up like the last session faster because we don't have much time. Yeah, any questions?
Do you assign an ID for each player there and record the data? Or if it's dynamic data, so how do you store it?
So coming to that, blackboards, actually blackboards have 3 different scopes of working. So first, the default scope is like a local. So it is actually local to a single AI character. You can also run a blackboard in global. So where the data is accessed by all the AI characters in the world. And there is a third one where you can make certain set of keys in your blackboard global and rest as private. So you can use that to communicate, like if you want to broadcast a message, so like if the threat level is increased in the world, you can use a global blackboard to send the information to all the AI characters in the world.
Right, so to answer your question, that it's probably implementation dependent. So if you are sharing your blackboard, then probably you would have IDs of all the players. But if you are not, if you are instancing the blackboard, then every player will own one. So you don't need to have that thing.
So you are using a rule-based approach like algorithm or?
Behavior tree is
So behavior trees is basically decision trees, right?
Yeah.
So obviously they are like, okay, if let's try something in the beginning. If that doesn't work out, let's try something else. Now, if this works out, again, this would have probably subdivisions. Try doing each of them. So you know, it's a decision tree basically. So this whole thing is used to make decisions only.
Okay, thank you.
Cheers, guys. Thanks.
Thank you.